Hello, this is Professor Werwath. I want to speak briefly today about DFX, which is a topic that was very popular maybe 15, 20 years ago, and I think it's lost some of its not relevance. Certainly it's as relevant today as ever, but it's certainly lost some of its momentum as it's become overwhelmed by other tools such as agile development and things like that. DFX refers basically to the design for multiple factors, multiple considerations when you are designing a product, when you're designing components, or designing even new technologies. So let's get started. The definition really is the DFX is designed for X, right? It refers to the method of considering different factors, such as manufacturability. That was the first one. The design for manufacturability was the hot topic before DFX superseded it. Manufacturability, assembly, which is the ability for that product to easily come together, cost, quality, and this happens during the product development phase, usually during the requirements phase. It emphasizes the importance of addressing these factors early on to improve efficiencies and effectiveness in the development process. So what you want to do is by factoring these things up front, you can avoid iterations of design later, which will reduce cost, reduce time, reduce effort on engineering by factoring all these things in up front, right? So types of DFX, right? Design for assembly. This focuses on the optimizing of the product design to simplify the assembly process, right? Reduce manufacturing costs, enhance product quality by considering ease of assembly, part count, and component interaction. DFM, on the other hand, aims to streamline the manufacturing process by designing products that are easier and more cost-effective to produce, independent of assembly, minimizing material waste, ensuring manufacturability without compromising product quality. So it's that focus on manufacturability and designing to those manufacturability standards. Ideally, your company has already set up those standards. DFSS, or Design for Six Sigma, really integrates the principles of Six Sigma or lean manufacturing into the product development process to ensure high quality and reliability. In other words, it focuses on reducing variability and defects in products by using statistical methods and rigorous problem-solving techniques. Some additional considerations, right? So this goes beyond the previous slide in terms of things like design for reliability. So every component you use in your product has an inherent bathtub curve, an expected failure rate over time. And what I mean by a bathtub curve is you have an initial fallout for reliability, those early infant mortality failures. Those tend to go away quickly. Then you have a long period of hopefully pretty reliable operation. And then as you approach end of life, you start to have the higher failure rate again. So if you look at it, it looks like a bathtub because you have this long performance of low failure rates flanked by two, the front end and back end of high failure rates. So Mill Standard 810C gets into this quite a bit. So if you really want to get rigorous about it, you can look at 810C and component by component model the reliability of your assembly and your product. Design for resiliency sounds like it should be the same thing, but it's not. Design for resiliency is about what happens when your product fails and how does your product respond to failure. What does that mean, right? So, for example, do you have a battery backup in case your power fails, right? Do you have a hot switch over CPU in case your CPU fails, right? Et cetera, et cetera, et cetera. So a single modem going into a system is not very resilient because that single modem might be providing critical information, and the failure of that modem could take down the whole system. So having parallel and redundant systems is one obvious approach to resiliency, but there are many, many others, right? Design for repairability and maintainability. Ask any mechanic how they like working on an engine, right? Can they access the parts? Can they replace the parts easily? Under what conditions does the engine have to come out or the transmission have to come out in order to, say, replace a spark plug, change the oil, change the transmission fluid, change a distributor, or change some part of the admission system. So, access to parts for repairability, access to components, access to the system without having to do significant disassembly, that's key, right? Maintainability, is the product itself maintainable? Can you replace critical fluids? Can you replace items that will eventually fail, such as batteries, right? If the battery exists on the motherboard of a computer, can you easily access it? Is it soldered in or is it socketed? Can you easily replace it without having to use a soldering iron? So things like that, right? Designed for reduced operating costs, right? So the interval of changing a fluid, if you double that interval, you reduce the operating costs, right? If you have a more efficient engine, you're using less fuel, that will also reduce the operating costs, right? Et cetera, et cetera, et cetera. So designed for the environment, this is huge. This is, I think, relatively new. This thinks about what happens at the retirement stage. What are you going to do with that product? Do you recycle it? Can you reuse it? Can it be easily disassembled? What will it do to the environment if it winds up in a landfill? How do you avoid going into a landfill, et cetera? So designing for the environment also includes the front end to say, well, where did the materials and components come from to build your product? So designing for the environment looks at the entire life cycle and actually understands what is the impact, both from a water perspective, a carbon emissions perspective, critical materials perspective, impact on landfills and water, water reservoirs, et cetera. So design for the environment is huge, right? Entire books have been written on this, right? Design for energy management. This is one of my pet peeves, but a lot of products do not allow themselves to be energy managed, right? So, I mean, your computer has a sleep mode, which reduces the energy drain. Not many products do that. Not many products are even aware of energy costs. So they're not able to adapt to various energy shortages or surpluses. Having built-in storage is one approach to dealing with an energy surplus, right? You can store it when it's cheap and then use it when it's expensive. The last bullet here takes a little bit more discussion here, but design for postponement. I know a lot of you don't even know what postponement is, but imagine a product that comes from a factory where the finishing touches are not done at the factory, but they're done at the point of sale, right? So some smartphones fit into this category, or laptops, some cars. There's a variety of products that fit into this category, right? What is the point of postponement? Well, it reduces the number of SKUs. If, for example, you have a computer that can accept 128 gigs, 256 or 512 gigs of memory, what are you going to sell? What if you sold just one version of it and left the adjustment of the memory to the point of sale, where you're literally just plugging it in at the point of sale? So that would be a postponement type decision, right? So you're making one standard product that can be customized at the point of sale instead of stocking 3 or 4 different SKUs and literally having to guess, well, how many 256s are we going to sell? How many 512s? How many 128s? Who needs what, where? What if they're short 512s over here, but they got plenty of 128s over here? Those sorts of issues go away magically if you have a postponement strategy that says, we're going to build one configuration and the memory is installed at the point of sale, and whatever memory the customer wants, we charge them the appropriate fee, we plug it in, and they're gone, they're done, right? It allows or requires a point of sale to customize the product prior to customer delivery. Like I said, computers, smartphones, cars with different wheel or trim packages. In some cases, the dealer can do the installation, right? Cars with different wraps. Everyone knows the Tesla Cybertruck is a brushed stainless steel finish, right? Not everybody likes that look, but that's the only look that Tesla makes. They only make one color. It's brushed stainless steel. It's not painted, so they're avoiding all those paint costs and all the hassles that come with painting and with protective coating of the paint. All that's avoided, right? The Cybertruck is streamlined in that sense, right? And the factory says, you want a color, you deal with it at the point of sale. So the customer can either at the point of sale or on their own get what's known as a wrap. These wraps have different colors, different textures, and you can literally wrap the vehicle in whatever color you want. And if you want to change the color later, remove the wrap and put a new one on. It's pretty easy. Not cheap, but relatively easy. Why would you do this again? It reduces the cost to manufacture, so you have fewer SKUs, and that saves money. The factory is more efficient. You're building fewer configurations at higher volumes and faster rates. The distribution is simpler because you have fewer SKUs to distribute. It's streamlined, it's higher velocity. And you don't have to guess what the inventory levels would be for the different configurations. I guess the word would be forecast, right? You don't have to worry about forecasting at that minute level. You're selling a Cybertruck. Who cares what color it is? It comes out of the factory as one color, right? It also reduces fragmentation in the supply chain. So you don't have to worry about, oh, the only red ones are in Iowa and only the black ones are in Missouri. Guess what? Everybody's got the same thing. You can make the color whatever you want it to be at the point of sale, right? So some best practices and strategies here. Employ cross-functional teams, right? Utilize computer-aided design tools, conduct design reviews, foster a culture of continuous improvement. I would include simulation and concurrent engineering into these practices. I'll talk about concurrent engineering in a moment. Best practices include early involvement. Early involvement is the underlying phrase here. Early involvement. Please, manufacturing, engineering, design teams, support teams, reliability teams, even the mechanics. I mean, United Airlines will get involved with Boeing at the early stages of an airplane design. They'll send their flight attendants, they'll send their mechanics, they'll send their fueling crews, all to understand what the new product is going to be from Boeing and how it can be best tailored to meet the needs of United Airlines. Just an example, right? Ford will do the same thing with their downstream suppliers to say, okay, let's bring the door manufacturer or the trunk manufacturer or the sheet metal people or the door handle people or the windshield people into the design process as they design the new car, right? They're looking for feedback from the stakeholders throughout the design process. If you're making it easier for your suppliers, then you're making it easier on yourself, right? If you're making a product that's easier to maintain in the field, you're making it easier and lower cost to deliver a high quality product. Concurrent engineering looks like this, right? So you have all these different disciplines, manufacture, assemble, market, investigation, materials, all working in parallel with each other, bringing the downstream functions into the upfront process. You're doing this during the requirements phase, and you're doing thorough testing and simulation to make sure that you're meeting those requirements, okay? Some of the benefits I think we've talked about, right? Cost reduction, quality improvement, time to market acceleration, and innovation boosting, right? So you're getting all of these advantages by using a DFX approach. Some case studies here, Dell Computer did a lot of this with streamlining their production processes by literally having their components and their major suppliers in the same factory as them, and literally, bringing them into that process of design and into the process of manufacturing. So the supplier is side by side with you in your own factory, right? Ford used some DFM approaches, design for manufacturability, by bringing in their suppliers into the design process. They started with the Ford Taurus. The Ford Taurus was notoriously efficient, both in the factory and in the field. Very well designed car. The original Ford Taurus was award winning in its day. And again, DFM was one of the main reasons for that, right? Some DFX integration, some increased product innovation can come from companies like Apple Computer. Have you ever noticed, and this is a very simple power supply for a Mac laptop, I guess the Macintosh laptop has a power supply that's external to the computer. Why is that? Think about it. They're selling these laptops around the world. Each jurisdiction has its own power supply requirements. 110, 120, 240 volts, different hertzes, 50, 60 hertz, et cetera. So and different plug configurations. So by creating an external power supply that can be, if you want to use the word postponement, that's fine, right? But it can be added into the production process at the last minute, knowing where that computer is going. A computer going to the UK, Germany, or the US, they will need different power supplies, right? They will need different configurations. Instead of changing the innards of the computer itself remains constant. It's getting its DC power from a consistent power supply that has different adapters and different range of operation, so it can accommodate those different needs for different markets. This is a classic DFM approach. I would also call this a postponement approach. So what's the future, right? Artificial intelligence to help build into the product certain features and functionality, virtual prototyping, sustainable design, digital twins, right? These technologies are set to revolutionize product development processes so that we don't rely on the engineers and their memory and their ability to foresee these things. You create a set of rules. In the old days, you would put it inside your CAD system. In the future, that CAD system will be enhanced with AI. And the AI will be almost like a layer on top of that that says, okay, these are the foreseeable results. How long will it take to change the spark plug on this engine, right? Ask the AI, right? You give it a design, you ask the AI, and the AI says, oh, 4 hours to change the spark plug. And then you say, what do I need to do to get it down to 40 minutes, right? And the AI says, make this change, move this configuration, maybe change the implementation. So these are the advancements of the future. This is how we're going to be reducing R&D costs. This is how we're going to be able to take R&D and apply it to a variety of different markets for a single platform, a single product. So with that, I hope that was helpful to you, and I want to thank you for your time.